Hey, does anybody know why Snoop carries an umbrella while it's raining? It's for drizzle. Shout out to you. I hope you enjoyed the video.
Come on now, dog. Come on, man.
What's going on, Stat Cats? You ready for another video? We are doing section 4-2 on the addition rule and multiplication rule. So here we go. I'm going to maybe show this in my class just as a little bit of comedy. If you grew up listening to old school rap like I did, we knew that Snoop was part of the Dog Pound. And so this section is about to be on compound probabilities. So I just kind of played along with some words there, the compound, and it kind of reminds me of the old school Drake meme. But yeah, let me go ahead and introduce you to what my plan is for section 4-2 on the addition rule and multiplication rule. In the textbook, this section, I want to show you that a good chunk of the examples for it are based on tables like these. Okay, so results from drug tests of job applicants. So here we have a table, pivot table, where the first row is for subject uses drugs, second row is for the subject does not use drugs. First column is positive test result and negative test result for the last column. So one thing that is built into this table is the concept of tests either being correct some of the time or tests not being correct some of the time. So you're probably familiar with the concept of something such as a true positive or a true negative, or a false positive or a false negative. So one of my examples that is similar to this one, I'm going to be somewhat required to explain what those sorts of notions are. So let me go back to my first page of the notes. And something that I saw a long time ago was this meme right here, which I think captures the whole idea in such a wonderful way. So a type 1 error is considered to be the false positive. And here we have a doctor saying you're pregnant to a man in a hospital bed. So we know that that can't happen. So right there would be a false positive. And here we have a type 2 error, a false negative. So it says you're not pregnant, says the doctor to the female that is clearly pregnant. Okay, so positive means pregnant, negative means not pregnant. And so if it's false that you're pregnant, then that is a false positive. And if it's false that you're not pregnant, that's a false negative. So that's what I'm going to be using to explain the concept here. And I decided to stick with the drug theme because one of the examples or one of the problems in the problem set reads like this. And I first started out with kind of the major idea here that a compound event is an event combining two or more simple events. Okay, so we're involving multiple events in this section, and we're going to be working with some famous rules for probability alongside it. So going back to this drug test here, I didn't want to just throw this at them right away. I wanted to give them some context and why this could be relevant to them. So I've taken a drug test for my place of employment, something that they require of all instructors, and the place that I went to is known as Concentra, and they test for a variety of things, THC, cocaine, and everything like that. And I don't use any of that. Okay, so I wasn't really nervous having to go in to take that, but for students that are looking for potential employment, their job might require it as well. So I think it might be a good teaching point and a good segue into the example that is going to kind of be the theme throughout the section here. So I took this from Concentra.com. Drug testing is an important part of the hiring process and routine maintenance of owning a company for many reasons. This is straight off their website. It's proven to be the best preventative measure in ensuring the safety of your workplace. Employee drug use increases the risk of an accident. Therefore, doing everything in your power to make sure it is not taking place in your company is crucial. And there's a little bit more verbiage to it, but I think this kind of nails the point home as to why some companies require drug testing. Now, drug tests aren't 1,000% accurate. All right, and so let's see here. Suppose a one-panel THC test for marijuana use was administered for a company, and the following results were found. Among 143 subjects with positive test results, there were 24 false positive, so incorrect results. All right. Among 157 negative results, there were 3 false negative, incorrect results. And it says use the information to construct a table. So I want to basically connect it to something that can happen in real life. You know, when you're taking tests such as a drug test, this could happen. Okay, so it could talk about the validity or lack thereof of a test. So what we're going to do is we're going to fill this table out together. So I scaffold it for them. So the first row, subject uses drugs. Second row, subject does not use drugs. First column, second column technically, positive test result, negative test result. So it's here where I'm going to have us fill out the numbers and then explain a little bit further what it means to be a false positive and a false negative. By the way, the opposites of those are true positives and true negatives, so the test correctly identifies those people in that case. And this segues us into some of the theory. So I made a segue note here. One may be interested in knowing the probability of the test yielding a false positive or a false negative, among other information that can be gleaned from the results. So in order to answer these sorts of questions accurately, we need some foundational formulas. And so that takes us to one of the 2 major rules in this section, which is the addition rule. Now, let me show you something that is going on with the author here. So the author is really bent towards developing intuitive understandings of the formulas, which there's no wrong in doing that. I think that's a great idea. So if you read through this section, oh, I forgot to say, this is the section from Elementary Statistics, 14th edition by Mario Triola. No, they don't pay me to say that. Shout out to the Coach Gang. Thanks for that info. So anyway, the author likes to really get wordy in this section and develops like an intuitive approach to understanding the formulas. He's very much against using formulas blindly, which I agree with that. So I pared a lot of this down because I think what he's putting here in terms of intuitive understandings and notions can really just be explained by you, the instructor. There's some other ancillary information as well, which I've kind of folded this into diagrams. I'm not sure why he doesn't use Venn diagrams, but I think it might be appropriate to use them just to give students a visual idea of the notion here. But the addition rule is let A and B be any 2 events, then the probability of A or B, and we're going to fill the rest out together, is P of A plus P of B minus the probability of A and B happening concurrently. So it says for P and B is the probability that A and B both occur at the same time as an outcome in a trial of a procedure. So in this first Venn diagram, I'm going to explain why the formula is the way it is. If you count the area in circle A and count the area in circle B, you're actually double counting the intersection part of it, and that's why we have to subtract P, the probability of A and B. And then I want to explain to them what it means to be a disjoint event. So you probably saw when I was scanning through the pages here that the author has a table on disjoint events and some quick explanations. So I might pull this out and show this on my document camera just to help sort out what it means for an event to be disjoint and not disjoint. But you could do that with the diagram as well. And with a diagram like this, the formula for P or B reduces to just P of A plus P of B. So then I go into an example where it says, using the scenario above as well as the table, answer the following. Okay, so what is the probability that a randomly selected subject had a true negative result? Express your answer as a fraction in reduced form if necessary. And then, if one of the subjects is randomly selected, find the probability that the subject tested positive or did not use marijuana. Express your answer as a fraction in reduced form if necessary. So this example requires us to reference the table on page 1, so you just want to make sure that this is correctly filled out. And then I phase into the multiplication rule. Now, this part I kind of struggled with just because of the sequencing of his presentation of the multiplication rule. So he first starts out with notation and then a caution about what P of A and B could mean, and that's a little bit confusing. And then right after that, he goes with the intuitive multiplication rule, which is fine, and then into the formal multiplication rule. So in my opinion, doing one of these right after the other kind of muddied the waters for me. And then, it's followed up with independence and multiplication rule. So this is just like information overload on this page, in my opinion. So if students are reading it, they might feel a little lost. So as an instructor, it's your job to recompile this information and present it in a way that makes sense to them. So here's what I did. I kind of came up with this where it says the addition rule is associated with the word or. However, the multiplication rule is associated with the word and. To build an understanding of how multiplication rule works, let's consider the following scenario, which will utilize a tree diagram as part of its solution. So the author actually does use a tree diagram towards the end of the section to explain the intuitive notion behind the multiplication rule. Let me see if I can show that to you guys. Yep, so the rationale for the multiplication rule, and then there's the tree diagram. I thought maybe it'd be a good idea to maybe introduce the tree diagram in the beginning of learning the multiplication rule. That way they understand the concept quicker, and it's more visual. So I had Claude, create an example where it's to do with basically just counting. So here's a sample. Mia is getting dressed for a school picture. She has 3 shirts to choose from, a red one, a blue one, and a green one. She also has 2 pairs of pants to choose from, black and khaki. If Mia picks 1 shirt and 1 pair of pants, how many different outfits could she put together? So I'm going to explain to them what a tree diagram is, and we're going to construct something similar to this. We'll count the number of ways, and then we can kind of phase our way into independent and dependent results. So I made a note as a segue. When applying the multiplication rule, we must consider whether the probability of event B occurring must be adjusted to account for the previous occurrence of the event A occurring. So I kind of leave that for them to just put a pin in, and then I give some definitions. Let A and B be any 2 events, then the probability of A and B equals, and so I'll give them the general version of it with the vertical bar. 2 events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. If A and B are not independent, they are said to be dependent. So here you can go back to the Venn diagram and say that, well, the probability of A happening does have some sort of influence on the probability of B happening. So here you can kind of make a connection as to, what they're trying to say in terms of events that are dependent. And then you can explain that if A and B are independent, then the probability of A and B is simply P of A times P of B. So I then had Claude add a layer of complexity to the t-shirt and pants example. I said, okay, can you create a scenario where we can use the general multiplication rule, still with Mia picking out a shirt and pants, but let's say that Mia is kind of a fashionista and likes to color coordinate. Okay, so if we're picking between black or khaki pants, maybe Mia likes red to go with khaki and blue to go with black. All right. So Claude kind of applauded me for that, not to toot my own horn, but I was glad that it liked the idea. And here's what it came up with. It says, okay, Mia has 3 shirts she reaches for. Red 50% of the time, blue 30% of the time, and green 20% of the time. But she's picky about matching. In particular, her pants choice depends on which shirt she's already picked. So with the red shirt, she wears black pants 70% of the time and khakis 30% of the time. With the blue shirt, she wears black pants only 20% of the time, khakis 80% of the time. With the green shirt, it's a coin flip. Black is 50%, khaki is 50%. What's the probability Mia wears her red shirt with khaki pants tomorrow? Round to 1 decimal place if necessary. As a hint, construct a tree diagram. And so I'm noticing here that I put the wrong tree diagram in this section of notes. There should actually be 3 boxes here, in which case that adds 2 more boxes to the right. So give me a moment to pull up Claude. Okay, so yeah, this is the diagram that we could actually use. Oops. Okay, so yeah, we can mark down the probabilities here. So let's see. So 50% red, 30% blue, 20% green. So we just mark these branches with the percentages. And then given the condition that she wears a red shirt, 70% of the time she'll wear black pants, so 0.70 there and 0.3 here. And so if we're asked, what is the probability Mia wears a red shirt with khaki pants tomorrow, it would be this probability times that probability. So you're kind of getting a visual of the multiplication rule in the general version of it, which is helpful. I'll be honest with you, tree diagrams really helped me with probability. So I'm definitely going to share that with the students. All right, so I'll get rid of this and put in the correct tree diagram later. Now, another thing that's mentioned in this section is sampling with replacement and without replacement. And I think it's kind of a good timing for that because when you sample something without replacement, it can impact the probabilities of your next selection. So that needs to be accounted for. And this is kind of prepping us for conditional probability. All right, like what's the probability of B given that A has happened? So kind of a wise choice on the author's behalf. So what I'm going to do is just tell them that the independence and dependence conditions can be altered when selections are made with replacement and without replacement. So what I'm thinking about doing for this in class is having a deck of cards, explaining what a deck of cards is, telling them how many cards there are, and then maybe having them use their intuition to figure out the probability of, let's say, selecting 2 club cards without replacement versus with replacement. So a good teachable moment right there. Small micro interactive thing that you can do. So now I'm going to refer back to the table on page one again. and we're going to practice those concepts. So it says if two of the subjects who use drugs are randomly selected with replacement, find the probability that the first selected person had a positive test result and the second selected person had a negative test result. Okay, so this is with replacement. So when you're finding the probability of the second selected person, your sample size doesn't change. All right. And then it says for part B, repeat part A by assuming the two subjects are selected without replacement. So here the sample size does change, so you have to alter the probability of that second selected person. And then to round things off, I saw an example that kind of ties into physics, and I'm a fan of physics. And then I noticed that when working out the solution to this one, you can use a tree diagram, so you kind of get a double whammy there. So you can reach the people in your audience that are science buffs, and also get an extra dose of making a tree diagram. And this is really inspired by us having some storms recently, and my youngest son has a pretty expensive gaming computer, and anytime that there's thunderstorms outside, my wife tells him you should probably shut it down because the power going out can fry the circuit board potentially. And so we have things called surge protectors in the event that that happens. So it says refer to the accompanying figure showing the surge protectors P and Q used to protect an expensive television. If there is a surge in the voltage, the surge protector reduces it to a safe level. Okay, so basically a surge implies that there's an abundance of something in sort of a haphazard and fast way. So when your power goes out, the electricity kicks back in. Sometimes it overshoots the limiting capacity that your electronics can handle. Okay, so assume that each surge protector has a 0.985 probability of working correctly when a voltage surge increases. If the two surge protectors are arranged in series, so one right after the other, what is the probability that a voltage surge will not damage the television? So basically, what is the probability that both of these are going to be working? All right. And the solution to it is a lot more intricate than you might believe. So you have to consider, the case where, P works, but maybe Q doesn't. So as long as P works, it doesn't matter if Q works. You obviously can have them both working. You could have P not working and Q working. But what you want to avoid is P failing and Q failing. So you can actually approach this in another way as well. You can find the probability of both these failing and then subtract that result from 1. So, that's really up to you. But, that's really it for this section of notes. I didn't really do anything all that fancy in terms of, Claude creating some simulations or some graphics. Claude did produce these for me, by the way, and I just altered them to look a little easier on the eyes. But yeah, so that's going to be it. Just a straightforward section of notes for this concept, and that's where this video is going to end. Thanks for making it through all the way. If you're still here, let me know if you have questions or if you want any of these materials. Otherwise, shout out to you, StatCats. Let's keep bossing up with some statistics. All right, shout out to the Coach Gang.